Hello and welcome to another video. This question sent by Phoebe. Great question, Phoebe. And it gives me a chance to use my complex numbers on it. And so, yeah, I'm just quite excited about doing this. It is not an easy question. It's one of these ones where the difficult bit, I mean, even the first bit's quite difficult because I haven't seen a question quite like it. It's interesting, but when you see what they're talking about, it becomes obvious actually. But it's not though. It's not obvious. This is not an easy question by any means. Part B's got this classic situation. How many times does this happen in further mechanics, where basically we're in this situation? Maybe we know E, maybe we don't. But basically, the situation is if it was flat and the vectors were all along this line, then it would be really easy to do because the component of the speed which is perpendicular to the slope is the only thing affected by E, but the component of the speeds parallel to the slope stay the same. And it's that classic situation of like, well, it's not parallel though to the vector, and so I've got to kind of like flatten it and then rotate it back, or I've got to use that cunning trick with I think Daniela talked about like minus E, I've never seen this formula before, but it makes a lot of sense. Minus I dot U E equals I dot V, or something like that. Basically using this idea that the slope is parallel, that the slope needs to be, you need to find the component of this vector acting parallel to the slope and the component of this vector acting perpendicular to the slope. That's what it's all about. That's what makes it difficult. But anyway, let's get into it. Let's get stuck in. Now, it's a really tough one because there's a lot they don't really make clear on the diagram. They have tried to make it clear actually looking at it. We know, firstly, reading it very carefully, that this slope is parallel to 3 minus I. So I'm going to put 3 minus 1 there, 3i minus j, sorry. What else have we got here? What's this? 0.51. Okay, point R is located on QS, so that the vector RT, right, okay, so I'm going to add another blooming line to this already confusing diagram. That is in the direction of a half 1. That's just in the direction of it, so it's really k times a half 1. Yeah, you need that actually for the first bit. The particle is projected across the floor, blah, blah, blah. The velocity of P is 2 minus 10 just before it hits at R. Okay, and it bounces off, and that's where it's bouncing off, yeah? Before striking QS for a second time. So it bounces off, it strikes ST, then it strikes QS. Now, given that the coefficient of restitution between P and QS is E, so this is E, find a range of possible values of E. Yeah? What a weird question, eh? Well, straight away we know that there's not much we know, is there? Like, we don't know this vector, which is kind of disappointing. But we do know actually a component of this vector because parallel to the slope the speeds remain unchanged. It's only perpendicular to the point of contact where E comes into play, and basically E is the ratio of that divided by that. Yeah, it's the ratio of rebound over approach perpendicular to the collision, the plane of collision. I hope I'm explaining this clearly. It is. I do find it tough to explain these tougher questions in mechanics. I really do. I get my words fumbled. Okay, so let's have a go at it. Well, like I say, we know actually that for this rebound, this must be vector 2, because that component's remaining the same. And then let's call this x, where x is, if we ignore the sign on 10, x is like whatever e times 10 equals. Yeah, in fact, let's write that down. X equals, well, if you like in more familiar terms, e equals x over 10. Yeah. But now let's look at this vector here, k at half 1. If this is steeper than that vector there, yeah, then it misses st, yeah, but we know it hits st, it strikes st. So the way they've got this answer is they've simply noted that the vector 2x must not be steeper, and I'm going to put that in inverted commas, and explain it a bit more, than the vector k, k times a half 1, yeah? It mustn't be steeper than that, because otherwise it misses t. Now, how can we ensure that? Well, if we make k, let's let k equal 2. Sorry, not k equal 2. Let's let k equal 4, purely because then I've got the same x component here. and then I can see that 2x must not be steeper than, because we don't really care about the length of this one, we just care about its gradient there, its steepness. So must not be steeper than. I'll talk a bit more about steeper, but it is the gradient. Than, right, if k is 4, then that's 2, and then that's going to be 4, yeah? In other words, now think about it, if this isn't steeper than this one, and 2, 4 looks something like this, yeah? 2, 4 looks something like that, then can you see that x needs to be less than 4? So x is less than 4, yeah? That's the way I'm going to put it. Now what is x? Well, x is 10e. So 10e is less than 4. And so e is less than 0.4, yeah? And then you've got a standard condition that e has to be greater than 0. So e is between 0 and 0.4. It can't be equal to 0 actually, otherwise it would be a perfectly inelastic collision, and it just goes dump like that, and it won't come back and hit this wall. So provided e is between those two values, it will go badunk like that, and eventually end up hitting S and T. So that's part A, and I admit I've never seen a question quite like it before. I can't remember. Maybe there are other questions like that and I've just forgotten them. That's possible, very possible. But yeah, interesting start to a question, and definitely difficult, definitely not easy. Okay, part B though. Part B is where the fun happens. Okay, they now tell you E is 0.3, which happily satisfies our condition, so that's looking more and more right. And so I'm going to put E equals 0.3 here. And on the other wall, E equals 0.2. Okay? Now really, I mean, it's worth 7 marks, this question. But really, when you break it down, how much is there to it? E is 0.3. And as x over 10 is E, we know x is going to be 3 here now, because, like I say, what is E really? It's just perpendicular to the slope. It's what happens if you do rebound divided by approach, when you take the component of the speed, which is perpendicular to the wall, on the rebound, and divide it by the component of the speed, which is perpendicular to the wall, on the approach, ignoring signs as well, because that's just telling you it's going down, that's going up. Well, 3 divided by 10 is 0.3, so x must be 3 now. So for part B, I can rub this out, and I can put that's equal to 3 now. Lovely. Let's draw it somewhere else though, because it's nice to have a nice picture. Now, what is really going on here? Well, we've got a vector. We know that it's 2, 3. But this isn't parallel, this components of this vector aren't parallel to this slope or anything. They're in normal 2 across 3 up, like that sort of thing. And it doesn't look to scale or anything like that. I appreciate that. But it's in, in this sense, it's 2, 3, x, y being the standard directions you would imagine. Yeah? And it's pinging off like this, and we've got to find this. Yeah? And we know E is 0.2. Yeah? Now, when you break it down, what is this question really asking you to do? It's asking you to, firstly, think about the component of the slope perpendicular and parallel to that wall. Oh, and let's not forget, we know, before I go any further, we know the direction of this wall is like 3 across, 1 down. Yeah, we know that vector. They told us it in the question. They also put it on the diagram. Look at this, 3 across, 1 down, 3 minus 1. I wrote it down up there. So we also know that. But all we're trying to do really is find the perpendicular component. And I might actually, can I, where's my rubber? Oh no, I didn't want to do that. I'll take this one away. I just want to do it in a different colour so I can talk about I don't know why I'm using colours. I'm colourblind. But okay, it's the yellow. I hope it's yellow. It's the yellow colour which is going to be affected by E, and I hope it's blue, maybe. It's the blue colour, which is completely unaffected by E and should be equal on both sides. Can I put it like that in the old way? That component of the speed should be equal. And we've just got to find this as a resulting vector. It just doesn't seem like there's that much, going, it shouldn't be that difficult. That's what it always seems. But it is difficult. I agree, it is. Okay, so what am I going to do? Can I do it my crazy complex numbers approach? Can you just allow me to do it like this, just this once, and allow me a little latitude to do what I want? Okay, what I'm going to argue is this. I need to rotate this. Now that's a 1. I need to rotate this in that direction. Yeah, to flatten it, if you like. The whole problem. I mean, rotate everything. That gets rotated, that gets rotated, that gets rotated. So I'm flattening the whole problem down. Now this would have an angle of theta, which is obviously the same angle as that theta. Now, you're well within your rights to use, by the way, this would be a perfectly valid way of doing it. You will definitely get the answer right, and I fully invite you to do it. In fact, let's quickly point out now what I'm talking about. To go into the formula booklet, booklety, Edexcel formula booklety, where is it? It's going to be somewhere here. And look up the matrix, because they give you this, don't they? So I totally understand if you want to do it this way. I don't, so indulge me for this once. But look up, anti-clockwise rotation. If you want to rotate it clockwise, just move that minus sign from there down to there. Yeah. If you want clockwise instead of anti-clockwise, work out what your theta is and do it like that. Maybe I'll do it like that afterwards, just to show you. It does give you exactly the same answer. Where are we? Let me just grab that. But you can do it like this, you really can, but I honestly think it's easier to do it the crazy complex numbers way. But there we go, maybe I'm just an oddball here. Okay, right, so we'll put that up for later. Yeah, maybe we'll do it like that in a second, but let me do it my crazy complex numbers way first. Okay, so I'm trying to rotate it like this. Now, how do we rotate something like that? Well, isn't that the same as saying I need to rotate it? Rotating this line like that is the same as rotating it like that, yeah? Which would be the same as taking the flat line and rotating it up like this. So what I'm saying is, basically, I need to rotate the whole problem by the vector 3 plus I, yeah, in complex numbers form. Because, let me just explain this. Remember, when you multiply by a complex number, you simply multiply the moduli and add the arguments, yeah? In other words, when you multiply by the complex number, r e to the I theta, you do make your vector a little bit longer by a factor of r, but you also turn it through an angle of theta. And that's why they're really useful. And what's more, I don't even need to use this r e to the I theta stuff, because what is the complex number I'm interested in? Well, I'm interested in the complex number which goes 3 across, 1 up, yeah? In other words, if I multiply this vector, written as 2 plus 3i, by 3 plus I, then I rotate it up and I flatten the whole problem. I will rotate this down because, if you think about it, like when we're rotating it this way, think of rotating it up so it becomes flat like that. This whole line is going to move up like that, in that direction. Basically, that's what you're doing when you multiply it by the complex number 3 plus I. Yeah, I know, I can see you watching at home and you hate this method. I know you do, but I'm going to make you watch it anyway, or you're probably fast forwarding it already to when I go through it with matrices. Let's hope I get it right both ways around. So anyway, all I really need to do is take my vector 2, 3, which I'm going to write in complex number form as 2 plus 3i, and I'm going to multiply it by 3 plus I, but I am going to be careful, because if I just multiply it by 3 plus I do actually change the velocity, yeah, because I multiply it by the modulus, and this modulus isn't 1, that has a modulus of root 10, so if I multiply the whole thing by 1 over root 10, yeah, that actually means that my complex number here now has a magnitude of 1, and therefore I'm not changing the magnitude of this number, I'm simply rotating it, yeah? So, let's flatten it. This is the flatten it stage, and it really is just multiply it by that. So, when I multiply it by that, I get 3 plus 11i, it's dead easy to do real quickly, because you get 6 plus 3i squared, which is 6 minus 3, which is 3, and then you're going to get plus 9i plus 2i, so that's plus 11i. Multiplied by 1 over root 10, don't times it through, there's just no point. Yeah. Now, only our complex components will be affected by the coefficient of restitution. And that's because when I've rotated it up, I've now turned the problem into this. It's now completely flat, and I've decided that this is my new speed. It's going to be 311, yeah, times by 1 over root 10 if you like. And now it's bouncing off, and I know E is 0.2. Well, what does E affect here? Only the Y components, yeah? Only the Y components. And so what's this vector going to be? Well, it's still going to be a 3, but the 11 is going to need to be multiplied by 0.2, becoming just 2.2. And I need to times it by 1 over root 10 still. And there's one more thing I need to remember, which is that the sign is going to change on the 2.2, and it's going to become minus 2.2, just because this one's going up and that one's going down. Okay, brilliant. Yeah. Now I've almost finished. I've now just got to undo the rotation I did. Yeah. Now how do I undo rotating by vector 3 plus r? Well, rotating by complex number with a certain argument, where my argument is this theta and this is 1, 3. Well, I multiply by not 3 plus I multiply by 3 minus I then, because if you take the flat line on the complex plane and you take the number 1, yeah, to rotate it by theta, I just multiply it by the vector 3 plus I, 1 times 3 plus I, and then I'll throw in a 1 over root 10 just to make sure it's still got a length of 1, yeah? And that will rotate it theta. Well, to rotate it in the other direction, I multiply by 3 minus I. Brilliant. Okay, so I know you're not laughing at home. Okay, so I've got 3 minus 2.2i, and I'm going to multiply that by 3 minus I. And now, don't forget, I've got 3 minus 2.2i times by root 10, 1 over root 10, but I've also got to times this by 1 over root 10, otherwise I'm going to change the length, I'm going to change the velocity, I'm going to increase it, and I don't want to do that. Now, the 1 over root 10 times the 1 over root 10 becomes 1/10. The 3 times 3 is 9. Then we're going to get plus 2.2i squared, but that becomes minus 2.2. So we get 9 minus 2.2, which is 6.8. And then for the i's, we get minus 3i minus 6.6i, which is minus 9.6i. And as you can see, that gives me 0.68 minus 0.96i. And so in vector form, yeah, our foray into the world of complex numbers is over. We can write this as 0.68 and minus 0.96 for our, what are they calling it, V2 or V or something like that, I can't remember. But I think that's the right answer, yeah? Now you're thinking, shut up about the complex numbers, I'm doing mechanics, why are you still going on about this? I like it, I'm sorry, I like it. Yeah. Now, there we go. That's the velocity of B when it strikes QS for the second time, because it's just coming down there. Okay, so you don't like complex numbers. You want to do it matrices. That's okay. I fully respect people who want to do this with matrices. That's absolutely fine. Much of my working is going to look remarkably similar, because matrices and complex numbers have a lot in common. You'll see when you get to uni, and you probably have even noticed now. I mean, look at this: cos theta plus I sine theta, cos theta minus I sine theta. What's really going on here? Okay, so I'll get rid of all of this, but we'll see if we get the same answer doing it like this. So what do I want to do? Well, first, to flatten it like that, I want to rotate it by theta once again, where theta is, can we put it like this, tan theta? Well, it's cos and sine we're looking at, really, isn't it? Like, we can easily work this out as root 10. Yeah, root 10 again, it's all the same stuff. Cos theta here is going to be adjacent over hypotenuse 3 over root 10. And sine theta is going to be 1 over root 10. Yeah, and we're rotating it. We want to rotate it by that theta, which is the same as that theta, and that is, let me just remind myself how a clock works, that is anti-clockwise, isn't it? We're going AC. So we can use this, yeah? So we can just multiply the vector 2, 3 by the matrix 3 over root 10, 1 over root 10, and minus 1 over root 10, 3 over root 10, and that will have the effect of flattening the vector. We're going to get when we do that. Oh, and who can spot the mistake here, eh? Yeah. 2, 3 should go on the other side. That was pathetic. Okay, right. 2, 3 should go over there. Otherwise, it's not possible to multiply it that way round. Okay, that times that plus that times that. We're going to get 6 root 10 minus 3 root 10, which is 3 over root 10. And then that times that plus that times that. We get 11 over root 10. And what that is telling us is that once you've flattened it, it's got a vector 3, 11, basically, over root 10. Yeah, I think I had the same thing last time, or something equivalent. I can't remember exactly what I had. I hope I've done it right. We'll find out in a second. Okay, so I've done that. And now I want to apply my coefficient of restitution. You still have to think in this, because what we're at now, you're probably thinking this is much easier, but we're at the stage where we've flattened it and we've decided that this is a vector 3 over root 10, 11 over root 10. Yeah, and so when it bounces off, the 3 over root 10 stays the same, but the 11 over root 10 we times by 0.2, because e was 0.2, so we've got 2.2 over root 10, but the one thing we must remember is it needs to be negative now. Yeah, and now I just want to rotate it back. Now, essentially, you take the inverse matrix to the matrix we used before, because that would be the opposite rotation. But the inverse of that is just basically move that minus down there. There's various ways you can explain that. I hope you understand that you just move that minus down there to do a clockwise rotation. So let's do that now, and then at the end we're going to do so 3 over root 10, this is a matrix, 1 over root 10, but negative, and then the positive 1 over root 10 here, and 3 over root 10, and I'm timesing that by this one, which is 3 over root 10 minus 2.2 over root 10. What does it give us? Let's have a look. Okay, what we got here? We've got 9 tenths minus 2.2 over 10. So 9 over 10 is 0.9, minus 2.2 is 0.68, I think. Hopefully, that's looking good. And then we get minus 0.3, minus 6.6, which is minus, over 10 though, which is minus 0.96, and voila! We've got both of the same answers. So there's two different ways of doing it, and interestingly enough, both ways are completely different to the way the mark scheme does it. This is an example of the u dot v, basically dotting it in the direction of the impulse. But first, and there's nothing wrong with this method, and it's a clever method, it really is. This is, do you remember me describing a fourth way of doing this, which I described as Sokotoa madness or something like that? You could do it like this. Personally, I don't like the look of it. I mean, look at that. Ugh. But yeah, if you did it like that, more power to you. But there we go. So loads of different ways of doing it, loads of ways of doing it wrong as well. Hopefully you do it right, but it is a difficult question. I hope you enjoyed the video, and all the best. Bye bye.